Welcome to another podcast. This episode we're going to be taking a look at our first sort of background topic for this section, and that is the topic of determinants. Determinants are sort of a key facet anytime you're working with matrices, which we're going to be doing pretty much for the rest of the semester. We're going to be considering mostly square matrices, so I'm going to be looking at, just to get us started with here, a simple 2x2 example where A consists of 2 rows and 2 columns. So this is a 2x2 matrix. Remember, when we write the definitions of these, the first number is the number of rows, the second is the number of columns. So this has 2 rows, 2 columns. Here are its entries, and this is a video about determinants. So what is the determinant of this matrix? I started with the 2x2 example because honestly, we expect you to know how to calculate the determinant of 2x2s if you're in this class, but let's go over it. The determinant of A is sometimes written this way, although you'll see a lot of people also just say determinant of A like this. And for this problem, they usually, rather than have square brackets or parentheses for the matrix, usually just have vertical bars when you're doing the determinant operation. And we've seen this before with the Wronskian earlier in the semester. But the determinant here is simply the main diagonal multiplied minus the off diagonal multiplied. And there's so many different reasons why that is important. One of the biggest reasons that is important is because when you start to look at the inverse of a matrix, then the inverse of the matrix A is defined as 1 over the determinant of A times a new matrix where I have flipped the main diagonal, so A and D switch places, and then you negate the off diagonal. So I take the opposite of B and the opposite of C. And so this is a formula for the inverse of a matrix, which will be handy for us. We're only going to look at the inverse of a 2x2 because finding the inverse of a 3x3 is very difficult by hand. But here's the other definition at this point, and that is the definition of a determinant of a 2x2 matrix. All right, let me just do a quick example with that. So let's find the inverse of the matrix A equals, let's see here, 4, -1, 2, and 3. Then according to the formula, A inverse is 1 over the determinant. The determinant here is 4 times 3, which is 12, minus -2. So minus -2 would be adding 2, so 12 plus 2 is 14. So the matrix now is switch the 4 and the 3, and then negate the off diagonal, which basically just means switch their signs. Then if I put it all into one piece here, I'd have 3/14, 1/14, -2/14, which is 1/7, and 4/14, which is 2/7. And so this would be the inverse matrix. Now understand that the reason that inverses are important is because if you have the matrix A and you multiply it by the matrix A inverse, the result is what's called the identity matrix. So let's just go ahead and show that. So give me a chance to talk about matrix multiplication. So if we multiply these two together, so remember the way that this works, you match row to column. So column 1 here matches with row 1 here. So let me just sort of color code this. These two will get multiplied. So this one will get multiplied by this one. And then this one will get multiplied by this one. And then you're going to add the result. So this is a 2x2 matrix. This is a 2x2 matrix, which means their product is going to be a 2x2 matrix. Remember, you can multiply matrices if the inside numbers here match, and then their product will be the outside numbers. So because the 2's match, I can multiply them, and then the outside numbers tell me that my product will be a 2x2. So the way that this works is first row here, first column here corresponds to first row, first column position here. So 3/14 times 4 is 12/14, and then 12/14 times, so this is 12/14, and then this is plus 2/14, it looks like, which is 14/14, which is 1. Then if you look at the position down here, you would take first column here, but second row here, so that would be 6/14 and minus 6/14. Yeah, 6/14 and minus 6/14. So this would be a 0. And then if you look in the top right corner, it would be the, since this is the second column, it would be second column but first row. So that would be 4/14, this one times this one, minus 4/14, which is 0. And then finally, so this is the second row, second column position. So it's second column, second row, 2/14, 2/14 plus, let's see here, that would be 12/14. So 2/14 plus 12/14, which would be 1. And so as predicted, what you'll end up here with is the identity matrix 1, 0, 0, 1. So the thing to keep in mind here is that anytime you do A times its inverse, the result of that operation is always the identity matrix of the same size. So this is a 2 by 2 matrix. So if the products are 2 by 2, then you get the 2 by 2 identity matrix, which in this case is 1, 0, 0, 1. That turns out to be enormously helpful to be able to calculate inverses, and we're going to use that to our advantage. But know that it relies on the calculation of the determinant. So looking at the formula for the determinant, one of the first things you notice is the determinant appears in the denominator here. So immediately that's going to tell us something. So we're going to start looking at some properties of determinants. So the first thing that tells us is I can't find an inverse unless my determinant is non-zero. So the first property of determinants that you need to know is a matrix A is invertible. What that means is I can find its inverse. So if I give you a matrix A, you can find its inverse. This is true if and only if, so this arrow works both ways. This is true if and only if the determinant of that matrix is non-zero. So the only way that you can find an inverse is if you have a non-zero determinant. All right, second property of determinants I want to talk about is that the determinant of a triangular matrix is the product of the diagonal. So it's the product of its diagonal elements. So what do I mean by a triangular matrix? Well, here's an example. So if this is the matrix A given by, we'll do a 3 by 3 matrix here, which are usually more difficult to calculate determinants for. It's called a triangular matrix because, as you can see, all of the terms lie either above or below the diagonal, so it kind of forms this triangular piece. So this is what's called an upper triangular matrix. You can imagine what lower triangular would look like. But if you have a triangular matrix, it says that the determinant of A is simply the product of the diagonal, and the diagonal here is 1 times 3 times -5, which would be -15. So this matrix has determinant -15. That's very nice to know. All right. Another property of determinants is, suppose that you have a matrix A that's n by n, and suppose that you have a scalar quantity k. In other words, it's a constant value. then I want to know what is the determinant of the matrix where I multiply A by the constant. Well, it's not just K times the determinant. It's actually equal to K to the N, because you multiplied each and every row by K, times the determinant of A. Now that's not something I'm going to prove, but it is helpful. If you have a constant that you want to bring out or pull out of each and every term, then to calculate the determinant of the matrix would involve, if you pull that constant out, you can't just say it's the constant times the determinant. It's the constant raised to the n power, where n is the number of rows or number of columns. So that's another sort of important formula to keep track of there. The fourth property here that I want to take a look at is another one of these that's very important. Suppose that A is an n by n matrix, so it's a square matrix. B is an n by n matrix. And then I want to ask, what is the determinant of A times B? So if you multiply two matrices together, what is the determinant of their product? It turns out quite nicely that it is the product of their determinants. So you can always do that. All right, last property. So for this property, the basic thing that I want to talk about is, well, actually there's a couple more properties here. So the next one is the transpose of A. So this term, or this T right here, stands for the word transpose. And what transpose means is that you switch the rows and columns. So if what was a row is now a column, then what does that do to the determinant? Well, it turns out that it does nothing. So switching rows and columns maintains the determinant. All right, last formula, or last property, if you will, and that is what happens if you take the determinant of two matrices added together. So if you add together two matrices, then the determinant, you would love it to be the sum of the determinants, but it turns out that it's not. So this is more of a don't do this than what to do. We don't actually have a great formula for the sum of two matrices and its determinant. We could come up with it, but it's nothing nice. It's nothing worth knowing. What is worth knowing here is that you can't distribute that. In other words, you can't take the determinant of each piece and add them together. That won't give you the value you're looking for. All right, so those are all properties of determinants. And I actually want to close by doing one more example. So far, all we've found is a 2 by 2 determinant. And I would like to see here if I can clear this area here. I would like to actually go in and find a 3 by 3 determinant. So let's talk about what that looks like. If you have, and I'll just do this with an example here. Suppose I have the matrix A that's equal to, I'm going to do a 3 by 3. So 1, negative 4, 2, negative 2, 8, negative 9, negative 1, 7, and 0. Okay, then the key to finding a 3 by 3 determinant is to look at, well, there's really no name to give it, so I'm not going to call it A, but I just want to look at the following. So I'm going to set up the matrix. I'm just going to copy it down. And then I'm going to add on two more columns, and the two columns I add on are going to be the first and second column. So I'm going to go ahead and write those two in. Not the third column, but just the first two. So then I'm going to look at this, it's not, well, it is a matrix. I'm going to look at this new matrix that I've formed. The determinant turns out to be the following. So if I take the downward diagonals, which are these. So if I take these downward diagonals and find their products, then the product of the first diagonal here is 0, because 8 times 0 times 1 is 0. And then here it's negative 36, and then here it's negative 28. So it's the product of those downward diagonals. And then if I look at the upward diagonals, the product of this is negative 16. The product of this one is, looks like negative 63. And the product of this one is 0. It turns out that if you take and you want to find the determinant of A, then the way to do that is to sum the downward diagonals. So you take the sum of the downward diagonals and you subtract from it the sum of the upward diagonals. So that turns out to be, let's see here, that's minus 64. And that is a minus a negative 79. So that would be positive 79 minus 64 or 15. So this has determinant 15. So this is just the way to find a 3 by 3 determinant. Now there are other ways, and I may mention one if we have a matrix that's suitable for it. The other way of doing this is something called the cofactor expansion. Cofactor expansions are really nice when the matrix looks a certain way. So if we run into this in class, I'll definitely bring it up. But for the most part, the easy way for you to remember how to do the determinant is what I just showed you. Alright, this is a little bit of everything. It's just sort of a brief introduction to determinants. We really only sort of scratched the surface of this topic. But it's going to be enough to get us through here the next couple of weeks as we start to dive into some of these matrix topics a little more thoroughly. Alright, thank you for watching.